I'm Brian Lantz, here to tell you about how to detect a gravitational wave and talk a little bit about the advanced machine that we've got. I always have to remember to tell people that LIGO is the Laser Interferometer Gravitational Wave Observatory. I've been saying it so long I often forget. The work I'm doing is not just me, obviously. It's on behalf of the whole LIGO scientific collaboration and the Virgo collaboration, which works out to be about 1,000 of my closest friends. So here's the sort of the who's who of the LIGO scientific collaboration. You can see Stanford's over there in the corner, and we actually run a number of detectors around the world. There are two in the United States, the LIGO Hanford and the LIGO Livingston Observatory. Advanced LIGO is now running at those two sites. Actually, it's down for work right now, but we have an agreement in principle with the government of India to place a third LIGO facility in India as a joint project with India, which is going to be great. And I get to use the stick. All right. There's a French-Italian collaboration called Virgo, which is in the process of upgrading their detector near Pisa. That's a 3-kilometer detector that's supposed to be running end of this year. There's a German-Scottish collaboration German-UK collaboration called Geo600, which has got either a very long prototype or a kind of a short detector in northern Germany, where a lot of our advanced ideas come from. And the Japanese are building one underground in Japan. The Australians have the beginnings of just the corner station for a facility. Anyway, it's a big network. And it's important to have a network for a bunch of reasons. Most recently, it's important to have a network because on September 14th, in the middle of the night, here and here, we saw the same signal come in. It looked like this. So signals from the noise should be uncorrelated. Signals from outer space should look the same. And so we saw this sort of orangey curve at Hanford and this blue curve in Louisiana. If you take they came in about 7 milliseconds apart, and there's some phasing issues, but if you flip them over and shift them by 7 milliseconds, you can see that those two signals line up very well. We think that's a gravitational wave. I'm going to tell you the rest of the talk, sort of how we did that measurement, a little bit about what we think that means, and then Rory's going to tell you more about the astrophysics of it. So one call out to the people doing modeling. So this is a model of what we think the event did. 10 years ago, I was at a talk and people were saying things like, we tried to model 2 black holes, but it sucked the coordinate system into the event horizon. And like, I don't even know what that means. Like, how do you do that, right? So about 10 years ago, they figured out how to actually simulate black holes going around each other. And now you can make very sophisticated models. Let me show you what that looks like. So here you got your 2 black holes. The background plane is a cut through space-time. The color represents the flow of time. So you can see underneath the black holes, it's going red. The flow of time is getting very slow as it gets into the event horizon. The arrows represent sort of the direction that space is moving. So we're about, 300 milliseconds before the collapse. You can see the gravitational wave signal running along here. It's about to enter the detector band right about now. And in a second, what we're going to see is that we're going to slow down the simulation. And you can see that space-time out here is nice and flat, the way we always see it around us. But by this event, space-time is not at all flat. It's nothing at all like flat. And then right there, when they combine to a single black hole, space gets very strange, and then these waves come off. And we're going to zoom back out in a second. You can watch the waves propagate out. Now the colors here represent sort of the intensity of those gravitational waves as they're going out.
Are you playing this movie on mute?
There's no sound in that movie. Wait for the end. I'll play it for you. I'll play it for you at the end, but you have to. I'll make sure everybody wakes up when I play the audio at the end. Not to worry. So, All right, so what is a gravitational wave? I think many people are familiar sort of with the media that's been going around. Newton described gravity as a force between objects that have mass. And the force is proportional to the mass and the distance between them. And space is kind of like an empty stage on which your Earth and your Apple sort of execute their gravitational motions. It's a great theory, but there are a couple of problems with it. One of them is that when this object moves, how does the information about where that object is, how does that get transmitted to the rest of the universe? Obviously, it can't happen immediately. So what does happen? And Einstein said, with his theory of general relativity, actually space and mass are hooked together. That space-time tells matter how to move, and matter tells space-time how to curve, is sort of how Wheeler said it. And you get these traveling distortions in the metric of space-time itself, and those traveling distortions are gravitational waves. I'm not going to try to explain GR any more than that, but maybe just instead give you an example. Right? If you've got an electron, it's got an electric field. If you accelerate the electron, it moves, and the distortions in that electric field travel out as electromagnetic waves. If you have a chunk of mass, it's got a gravitational field. If you accelerate the mass, you get distortions in the gravitational field. Those distortions travel out, we think, at the speed of light, and those are the gravitational waves. There are two important distinctions between electromagnetic and gravitational waves. One is that electromagnetic waves travel through space. Gravitational waves are actually a distortion of space and time itself, which is really weird. And the other is that space is very stiff. It does not like to be distorted. And so you can put a tremendous amount of energy into a gravitational wave, and you won't distort the metric very much, which is what makes them so hard to see. Now, I told you about sort of the little distortions in the space-time. Let me play the second half of this video again. If you look right here in the field near the black holes, as they start to collide, you'll see some of these rippling distortions. Right now, watch this field, and you can see those little fields kind of propagate out. You see the colors moving out there. Anyway, I love that video. I think that's cool. All right, so when the waves get to us, how do we measure them? Right? So what happens is you've got some binary black hole system. It's going around and emitting gravitational waves. When the waves get to us 1.3 billion years later, they're much smaller. And the way they manifest is a transverse wave. So if the wave's coming in towards you and you have a ring of particles, as the wave comes through, the ring gets distorted into an ellipse. The ellipse oscillates back and forth like this. All right, so you can see Dr. Smiley is getting distorted. If there's a big gravitational source in the back of this room and it came towards me, I get stretched one way and compressed the other, and I kind of get distorted like this. Of course, not nearly that much. The reason that gravitational waves are hard to see, as I said before, is that space doesn't really like to stretch, and that's why it's taken us so long to finally measure one, right? I mean, Einstein predicted these back 100 years ago. Ray Weiss in 1973 wrote a paper saying you could actually measure these if you took a Michelson interferometer and replaced your oil lamp with a laser and you made the arms really long. And it would still be hard. The signal that we saw produces they produce a strain. The strain that we measured was 1 part in 10 to the 21. So if you take the distance from the Earth to the sun and you distort that with a strain of 10 to the minus 21, it's the size of an atom. Right? So that little fluctuation, the size of an atom between here and the sun, that's what we measured. We actually had good signal to noise on that too. So we were able to pretty accurately measure that. So how do we do that? Sort of there are three kind of classes of things we have to do to make a measurement like that. The first is you want really long arms. So if you're measuring a relative distortion of space, the longer the thing that you start with, the more absolute length change you get. And that allows you to get rid of, to sort of see past a lot of noise sources. So we have a 4-kilometer long vacuum system. It's the world's largest ultra-high vacuum system by how much stuff we don't have. It's a 4-foot diameter pipe, 4 kilometers long. And it would be longer, but we couldn't afford it. So that's what we've got, really long arms. The second thing we do is you want to measure the distance between the mirrors very accurately. So here's a slightly more complicated version of the interferometer. You got your laser, some stuff, a beam splitter. You got these 2 long arms. And you want to measure, you don't actually measure the distance from the beam splitter. What you do is you measure the distance between mirrors at the input and the mirrors at the end of this long arm cavity. So first thing you do is you make that's a big Fabry-Perot cavity, finesse about 450. So you bounce the light back and forth in that arm a bunch of times, and you collect as much optical phase on that light as you can for your passing gravitational waves. You get as much phase per strain as is reasonable. And we end up, I'm not going to talk about this very much, but there's a limit sort of on the fundamental sensitivity. We've got 100 kilowatts in that arm right now. We're going to jack that up to almost 750 kilowatts by the time we're done. So you bounce the light back and forth in the arms, you pick up a lot of optical phase. Actually, you don't pick up very much optical phase at all, but you pick up a little bit. And you bring the light back out to the beam splitter. And here it turns out that at most frequencies, you're limited by your ability to measure the phase, by just the quantum mechanical counting statistics of looking at those photons. So if the thing that limits you is the photon counting statistics, the shot noise, then what you want to do is have as many photons as possible. So we put in a big laser. We think of this as our big, scary laser. Out here at NIF, it would be kind of like a little toy baby laser, but still, we like it. We're putting in 23 watts right now for our first observing run. It should move up to about 125 watts by the time we're done. And for those of you who are laser noise geeks, the laser frequency we lock to the common mode length of the arm, so the average length of the arms. And we can stabilize the laser frequency noise at 10 hertz to be 10 to the minus 7 hertz per root hertz, which is, I don't know, there's probably 2 people in the room who think that's cool other than me. But there we go. All right. Here's a picture of our laser built by the folks at Zentrum Hannover, our German colleagues. This is their German government contribution in kind to the LIGO program. But that's not enough power. Right? It puts a lot of power, but it's not nearly enough. So what we do is we play another optical trick. We set up the interferometers so that almost all of the light, when it comes back to the beam splitter, comes back towards the laser. We call this our common mode port, the symmetric port and the anti-symmetric port. It's set up so that the gravitational wave signal is going to be coming out of the anti-symmetric port, and just raw power is going to be coming back towards the symmetric port. So if you shine a laser in here, and it all comes back at you, you can think of this whole thing as a mirror. It's kind of a complicated, expensive, very large mirror, but it's just a mirror. And you can, again, build a resonant cavity to store the power with our power recycling mirror. And so with 125 watts, well, 20 watts going in now, we can store about 800 watts in this power recycling cavity. That's the current power. By having a lot of power, then at your beam splitter, you can very accurately measure where you are on that fringe. Here's a picture of that big German laser. People can ask me questions about how it's working. And there's a small commercial laser here, a 2-watt, 1-micron laser. It's got a master oscillator power amplifier. And that's what we used for initial LIGO. For advanced LIGO, we're going to put it into this injection-locked oscillator to get the 125 watts into the interferometer. All right, long arms, good sensing of the distance between the mirrors. The third thing you got to do is you got to keep the mirrors very quiet, right? So we can't tell the difference fundamentally between the mirrors moving and the space between the mirrors distorting, right? So got to keep the mirrors quiet. Here's our end mirror. This is what it looks like if you were to kind of peel off the building. You'd see the vacuum system inside. There's our beam splitter, the 2 input mirrors, and the end mirrors. And if you open up one of those vacuum chambers, you can see sort of the system we have to hold the optic. To give you a sense of scale, this post right here about 8 feet tall. It's about that big. So this is a big chamber. Here's the mirror. It's a 40-kilogram piece of glass. I'll talk about that in just a little bit more in a minute. At 10 hertz, the motion of that mirror should be 10 to the minus 19 meters per root hertz. And if we do it right, that will be set by the thermally driven motion of the optic. That mirror is a 4-stage suspension. It's hanging from an optics table, which is inside the vacuum system right here, which is on a 2-stage hybrid active-passive isolation system that I designed, so we'll talk about that a little bit more in a minute. The motion of this optics table should be less than 310 to the minus 12 meters per root hertz, and controlled all the way down to 0 frequency. And then on the outside, it sits on a hydraulic system. The motion up here is about 410 to the minus 10. So from here to here, you can see we've got a lot of isolation that we need to do. So how do we do that? Here's another picture of the quad suspension, a 4-stage mirror. We do this because each stage gives you passive isolation. So you get f squared of isolation from the stage ahead of you. And by the time you get 4 of them, and it's this long, you get sort of 10 to the 6 to 10 to the 7 isolation. I brought a prop. So to demonstrate this, I brought a scale model of the advanced LIGO optic, as you can see here. And it's hanging on a suspension. Of course, if you move the suspension point at low frequencies, what you see is that the mirror just kind of follows along. Bad thing about suspensions is that if you move the suspension point on the resonance, the mirror moves a lot more than the suspension point does. There's a lot of controls around the suspension to control those modes and point the optic. But the good thing about a suspension, if I can do this, is that if you move the suspension point at high frequencies, the mirror can't keep up. And so you can get isolation between the suspension point and your optic, and you can do it both horizontally and vertically. And of course, if some is good, then more is better. And so you can make a double suspension. This is why it helps to be tall. Let's see if I can do this. And so you can start moving the suspension point at high frequencies. And you can see that I'm moving my hand a lot more than I'm moving the optic. And
you could be playing disco music.
Yeah, that's right. Well, you know. Anyway, so there's your suspension. And they work remarkably well. By the time you get down to the mirror, as I said, it's a 40-kilogram piece of high-performance glass. It's 34 centimeters in diameter, 20 centimeters thick. It's about that big. It's got the world's best optical coating on it. And to be limited by thermal noise, one of the things we do is we keep the mechanical cues of that optic to be very high. And that concentrates the thermal energy at the resonant modes. The way we do this is kind of neat, I think. These are glass fibers that hold the optic and what we call the penultimate mirror. And so there's these little glass pieces that are bonded onto the piece of glass, these little ears. And then there's a glass fiber that gets welded on to those ears. And so when you're done, the optic and the penultimate mirror are effectively a single piece of glass. To give you a sense of scale of how big the thing is, I've included Betsy Weaver, who's the lead suspensions operator up at Hanford, next to one of the engineering prototypes. There's the sort of the stand-in for the mirror. This thing is over 2 meters tall, up to the optics table where it attaches. The optics themselves, when you replace the piece of aluminum with a piece of glass, of course you have to wear all these bunny suits, so you can't really see that everyone's as happy as Betsy is. But here's a picture of those optics installed in the vacuum system. Those optics are suspended from a table. The table is something that we designed at Stanford with a bunch of other people. And it's a 2-stage sort of hybrid isolation system. This bottom part is the second stage. That's the optics table, and you hang down. It looks actually very much like in any other optics table. It's a big piece of metal with a bunch of holes drilled in it with screw threads, except it's much quieter than most of the other ones, and it's up above you, and you have to attach things to the bottom of it. This is the first stage. You can see there's a spring that holds the mass of the first stage. There's another spring here that goes from the first stage to the second stage. And when you turn it on, you get performance that looks like this. So this is an amplitude spectral density plot of the vibration of a couple of the layers of that stage. And so here you can see at 1 hertz, the ground motion is around 10 to the minus 9 meters per root hertz. I'll get my stick now. There's a big peak right here at the microseism. This is caused by ocean waves crossing. This is at Hanford, so this is the Pacific Northwest. The green is the motion of that second stage. You can see at 1 hertz, we're down by a factor of a little more than, well, somewhere between 10 and 100. The purple curve is the suspension point motion. It's where the optic is actually placed. So you can see here at 1 hertz, the motion of the suspension point is at 10 to the minus 11 meters per root hertz. So 10 picometers in a 1 hertz bandwidth. Around 1 hertz is the vibration level of that table. And then out here at 10 hertz, we're actually down to almost 10 to the minus 13 because my clever operator Jim got our feed forward running. I'll tell you about that in a second. So this is the kind of plot that makes me happy because it means that my machine is working. It's a signal processing conference, so I threw in a couple of pictures about signal processing. So an example of something we do for signal processing. To get isolation from these stages, we use both active and passive techniques. The passive part is that the stages weigh several hundred kilograms, up to 1,000 kilograms each, and they're on a spring. So you get passive isolation above a few hertz. But we also get active isolation. We have control systems and a variety of sensors put through this thing. So here's our post. Here's an external hydraulic system. Here are the 2 stages of the internal seismic isolation system. Here's Dan Clark for scale, one of my former graduate students, with a variety of the sensors. So on the ground, we have these low-frequency Streckheisens. I saw there were some geophysics people in the audience earlier, so you guys will probably recognize these as sort of the state-of-the-art low-frequency ground sensing for teleseismic earthquakes and such. We have L4Cs. These are sort of small 1 hertz passive geophones. We have Nanometrics Trillium T240s, which is like a Streckheisen. You notice it has about the same shape and suspiciously similar colors. So you think maybe they're aiming at the Streckheisen market. We mount those inside the vacuum system. And then on the final stage, on the second stage, we have these GS13s, which are very high performance 1 hertz seismometers. And then we try and hook all that stuff together. Now we have both these inertial sensors to tell us how much the stages are moving, but we also have displacement sensors that tell us where the stage is. Because it's important not just that we do isolation, but also that we do alignment, because the mirrors have to be, for instance, pointed at each other. So on each stage, we combine the displacement and the inertial information in a little feedback loop, sort of local feedback loops on the 3 stages. But of course, that's not enough. We then put in, for instance, interferometric control to the displacement sensors on HEPI. When the moon goes overhead, it causes all kind of trouble. So you need to have this sort of control over HEPI. What happens is it's a resonant interferometer arm. So the distance between the 2 mirrors and the 4-kilometer arm has to be fixed. But 10 to the minus 13 meters RMS when the control is all turned on. But when the moon goes overhead, you get tides, as everyone knows. What's less well known is that the ground also moves up and down, not just the water, but the ground moves up and down by about plus minus 6 inches. And as that bulge goes past, you get stretching of the ground, about plus minus 120 microns over those 4-kilometer arms. And so as the ground is stretching out, you have to push the mirrors back and forth against the ground to keep the distance between the mirrors fixed. So by offloading control from the interferometer to here, we can provide that kind of performance. We measure the ground motion. If you know that the ground is moving up and you tell your platform, well, move down, then the absolute motion of the platform can be reduced. So we use this Streckheisen information from the ground. Anyone who's ever used a Streckheisen on the ground knows that the worst thing about the Streckheisens on the ground at low frequencies is that when the ground tilts, the sensors get confused. And we actually have, I believe, the world's best ground rotation sensor mounted in 2 of our chambers, next to 2 of our chambers in our detector to correct for that. We can then use feed forward from these sensors up to these actuators. We can do more of this sensor correction from stage 1 to stage 2 and more feed forward. I think in light of the time, I'm going to just say that that's the kind of signal processing we have to do. We do that actually in 6 degrees of freedom for each of these stages, for each of the mirrors and the advanced detector. So it's a lot. Each one of the individual loops is not particularly sophisticated. What's hard is to keep track of it all. And so we spent a lot of time talking about how to do that. When it's working, what you see is a single monitor on the control screen that looks something like this. This is the range on a day about a week after the detection. So we weren't expecting black holes, so this is the range to a neutron star binary system. Over the course of a day, you see we started at about 60 megaparsecs, which is kind of mediocre. The alignment is drifting. If they finally lost the lock of the interferometer, kind of messed around with it for a couple hours, got the thing realigned, got it back up to about 70 megaparsecs, and continued on for the rest of the day. This is an interesting plot, not for what you do see here, but for what you don't see, which is that at hour 15 and then again at hour 18, a big train went past the mirror in the Y end station. This is the band-limited motion of the ground in the 1 to 3 hertz band. So you can see there's this train rumbling past, but you see it on the ground, but you don't see it in the range for the detector, which is great. It's great. Rory's going to tell you about like glitching and non-stationary performance, right? This is the kind of one of the many things we try to get rid of. But as I said, we had very high performance sensors on the optics table, right? So how do you know? How do you know that that train didn't actually mess you up? People say, well, we look at the ground sensors, and which is true, but more importantly, we can actually look at the sensors throughout the seismic system and through all of the other subsystems as well. So this is a spectrogram from about 0.1 to about 10 hertz over that same 24-hour period, spectrogram of the motion of the seismic table. And you can see there are these little ghosts for the train right here and right here. They're pretty small. And up here in the detection band above 10 hertz, you see that there's just nothing of interest to see up here. So this is at the sort of 10 to the minus 11, 10 to the minus 12 meter per hertz scale. This is a funny plot. This is the spectrum, the ASD of that ring down signal. 10 to the minus 19 meters, 100 hertz, a couple hundred hertz. This is how much the suspension point would have to move to give you this much motion at the optic. 10 to the minus 4, 10 to the minus 6 meters out here at 100 hertz. You can take a time trace for what it would have to look like. It looks like this. It's almost unbelievable, really, because if you look at the scale of this is 3 meters, right? I can assure you my system is no longer linear at 3 meters of motion. On a good day, what you see is a spectrogram that looks like this, right? So here's my table on this is what they call in a paper a typical day. So this is a Saturday, like after Thanksgiving, right? So it's very quiet. And you can see that the motion in here on the seismic table is down here at the 10 to the minus 12, 10 to the minus 13 meters per hertz level. So much, much less than you would need to shake the mirrors enough to confuse the detector. And this looks really nice and quiet. One of the nice things we do with the signal processing, though, is that you can normalize this. Instead of looking at absolute motion, you can say how much is the motion changing, and this plot changes into something like this, right? So there's a little bit of yellow right in here, a little bit of funny signal in there, but you can pull it right out with not very sophisticated techniques and see that so right here maybe there's something at about 0.1 hertz. This is probably the microseism rolling up. These might be wind gusts coming in. Lord knows what that is. And then you can look for correlations between these kind of glitches in the monitors of the instrument and in the actual output of the instrument to give you powerful diagnostics about what's going on and what is real and what isn't. All right, everyone needs to wake up now. So now I'm going to finish off by playing the signal. This is a spectrogram of the 2 sites, about half a second of data. I'll turn it on. You'll hear sort of the noise of the instrument, sort of what it sounds like when there's no signal. It's kind of a and then you'll hear the chirp. It plays through twice at the real band, just band passed. And then it plays through twice more. We've frequency shifted up a little bit to put it more in the audio band. Then we'll do that, play it again. Ah, thank you. It's either whoop, whoop, that's why we call it a chirp. All right. Thank you. All right, so that's what we got. And then you can start trying to draw astrophysical significance from that. So here are those, again, the two signals that we saw, the best fit waveform and the noise. You can sort of compare the signal and the noise. It's a pretty big signal for what we saw. When you run through the numbers on it, and Rory will talk about this, I think, in some more detail, you can pull out numbers like what was that event, right? So 2 black holes, 29, 36 solar masses, so big black holes. Actually, we didn't know that there were any black holes of that size before. The final mass was 62 solar masses, and if you're doing math in your head, you'll realize that this is 65 and this is 62 because 3 solar masses worth of energy were radiated away from that event, which means that for a few milliseconds, there was as much energy coming off of this single black hole binary as there was 50 times more energy from that than there was from the starlight from all of the stars in the visible universe. Just astonishing, right? And it might, some discussion about this, it might not have caused any electromagnetic signal. It might be that the only way to see this is with a gravitational wave detector. Now, of course, we hope to get coincident data. And then once we get running again in the fall, you can say, well, we've seen one so far. The rest of the data from 01 is coming out soon, and this paper says that we should maybe see 1 or 2 more events. As you increase the range and the time, the amount of volume of space that you can see goes up for our second and third observing runs. And so you can make wild predictions about how much you're going to see, anywhere from like 2 to, if you're incredibly optimistic, 100. I kind of aim this way for how many more black hole events we're going to see starting next fall for the 6 months after that, and then into the future. With that, let me stop.